Hello and welcome to this introductory video on refraction. In this video we're going to take a look at this fundamental interaction that a ray can have when it's moving from one medium to another. So the fundamental and important starting point when discussing refraction is that when light enters a medium, it actually slows down. And it slows down by an amount dependent upon that medium, and conceptually you can think of it as the fact that in the vacuum, light is moving nice and easily, unobstructed, unhindered by anything. But secretly we know that that's oscillating electric and magnetic fields, so if you start putting other things in the way, then those fields are likely to interact with whatever's in the way, and maybe you can see how that would slow things down, that the field, the wave, cannot actually propagate at the normal speed because it's got to actually produce a response and continue the wave through this medium. So what happens there is basically any and all mediums possible will slow light down through this extra interaction. We quantify exactly what's going on with that medium by something which we call the index of refraction, n. And we say that what it does is it changes the speed of light in the medium, so we'll call that v, and it changes it to be c, the speed of light in vacuum, divided by my index of refraction. And since everything has to slow down light compared to the vacuum, we know that the index of refraction will always be greater than or equal to 1. It'll be equal to 1 if you're talking about vacuum, because then you get v equals c, and then when you put anything else there, the index of refraction will be greater than 1, as it's slowing that light down. So these indices of refraction are useful in determining how rays will change. So first off, what this one is telling us is that when we have this medium with some index of refraction n1 over here, and we transition into n2 over there, then what's going to happen is I've got the ray coming in at some angle with respect to the normal. So there's my incident angle. Then, and in this case, I'll actually, instead of calling it incident angle, I will redefine that as just being theta 1, the angle of the ray with respect to the normal in medium 1. Well, what's going to happen, it's going to bend either towards or away from the normal on the other side. So maybe I will come out like that, say. Okay, and exactly what angle I get here in this second medium, so I'll call it theta 2. That is what we were thinking of basically as sort of our outgoing angle earlier. If I call that theta 2, well, then basically I've got this nice relationship. It can be shown that n1 times the sine of the angle in that medium, 1, so sine of theta 1, is equal to n2 sine of theta 2, as we've written there. So this is quite interesting and requires a little bit of thought to understand why this should bend. So let me quickly make a detour into that and then return to some quick summary of what you can do as shortcuts of this. So here is a diagram, and what it shows you is, say you were considering a nice set of waves, as we were doing when we were drawing things for like the Doppler effect, etc. We've drawn a bunch of wave fronts over here, and as these wave fronts are moving, you can see what happens. They encounter this medium. They're moving with some velocity inside one medium. They encounter this boundary actually, and at the boundary they have to slow down or speed up. In this case, we're showing them slowing down. And as you see, as they slow down, these waves now get closer together on this other side over here. And when they're getting closer together, you can see that that results in them actually bending towards the normal. And on the other hand, if they were able to go faster because n2 was actually less than n1, then you would see that they bend away from the normal. So that is what this little point is reminding you of. This is the nice diagram to bear in mind for that, of why it's happening. That's where this equation comes from, and that's also where this little shortcut comes from. And this works even if you're not thinking about these circular waves. So here's another diagram really quickly to show you that. If you just look at these plane waves which are moving, then as they encounter this other medium, you see them slowing down and therefore, again, bunching up and resulting in what appears to be the perpendicular to the wavefront has now changed direction, and the perpendicular to the wavefront is really what we are describing as our ray.